Oopsies. All right, is this looking okay for you?
Yep, it looks good.
All right, thanks, Randy. This is part 2 of the doubleheader presentation. I'll try to make this go as quick as possible here. There's a lot of loops and a lot of images here. So for those of you who have known me anytime in the last 5 or 6 years, tornadic debris signatures has been something I've been very interested in, especially with dual pol coming online and trying to figure out, what really is a tornadic debris signature. And that's been a question that's been hounding us for a while there. And I would argue that the way we look for TDSs might be better suited by looking at the behavior of them versus just certain product thresholds. So if I were to ask you what a TDS is right now, most of you would say it's a lowering of the CC with a couplet in an area of reliable reflectivity. And to that end, that's been the definition of a TDS ever since it was coined 18 years ago, after the 99 Norman tornado. And there's been various, you'll notice right away that there's really no set agreement in the various research studies that are out there as to what that threshold for the various products should be. There's been a gradual relaxation in the reflectivity threshold all the way up. The latest study, one of the later studies I found by Vandenbroeke, had the reflectivity as low as 20 dBz could be used to classify a signal as reliable. One of the big linchpins that all these studies hinged on was the need for an SRM couplet. Remember that as I go in the next couple of slides here. And even correlation coefficient has varied quite a bit, even to the point where the Vandenbroeke study said that there's deviations allowed. So he's explicitly stating that these things don't fit into nice, pretty bins like we thought they did. And if you look at a timeline of 88D upgrades versus the TDS research I mentioned above, and this is not an inclusive research study, I know there's been more, but these are the big ones. Notice that a lot of them took place prior to the advent of sales, mesosales, and MERL. So suddenly, really, we're looking at a whole different data set now when it comes to radar data than these studies had access to. So maybe the need is to look again at, with these higher temporal data sets, is there a need to change what the EF scale, what TDS, what we call a TDS. Sorry, my mind's still on the storm survey talk. So we need to ask ourselves for a few seconds, what is really physically going on with a TDS, with a tornado debris signature? So in this example, we have a supercell and we have our tornado hooked up with the mesocyclone. And what happens is the initial tornadic debris rises very quickly with the tornado vortex and the mesocyclone. And on radar, it appears as a semicircular area of a CC minimum. And as time goes on, overall, they're owing to centrifuging and storm relative flow through the supercell. The debris cloud begins to expand and spread downwind. It's easier to see this spreading out at a single radar scan versus multiple radar scans. So I would argue that it's a lot more recommended to look more emphasis on temporal trends of the lowest tilts versus vertical tilts. And overall, over time, once the tornado is dissipated, the visibility of the plume begins to widen and spread downwind and eventually dissipates. And for anyone who looks at this, should look very, very familiar, because this looks like any smoke plume or high split run plume that you've ever seen. It behaves just like one of these types of plumes. So, and the visibility of this plume is going to depend very much on the environment. So TDSs behave like a plume. So let's stick with that first. And again, we're going to go back here real quick to TDSs versus tornadic circulation, because they're very different beasts. And for any warning meteorologist out there, you know that we really rarely sample an actual tornado scale circulation with the 88D, owing to the fact that our beam width gets too broad within very, very short distance away from the radar. And if we do happen to sample, it's usually just a couple gate-to-gate couplets at best. So usually we're sampling the mesovortex or the mesocyclone, if indeed it is present. And some of the latest research, I know I've been talking with Jana Hauser about some of her research, is showing there's a building body of evidence that tornado genesis is bottom up regardless of your storm mode, whether it's Supercell, QLCS, Landspout, it's all bottom up. with the vortex column being rapidly stretched and amplified via the updraft, mesocyclone, or mesovortex. And I underline updraft there because updrafts may not be rotating. So the light TDS particulate matter can be easily advected throughout the storm and grow much, much larger than the actual tornado scale circulation or even the mesocyclone scale circulation that is there. So weighing all of that together, this is a big point here, is that it may be possible to see TDSs within a region of favorable tornadogenesis without the need of a couplet being there. And this is especially applicable to Landspout, QLCS, and even LP supercell modes. So putting that all together, let's look for the plume. And we start off with the shape of the signature, looking for a semicircular area of depressed correlation coefficient. The differences between the ambient environmental CC and the TDS can be as little as 0.03 to 0.05 in the CC, so it's very, very subtle, but it sometimes can be picked out. In cases of low precipitation environments, you sometimes have to go back and rely on your old trusty debris ball that was coined back in the early 2000s, where you can actually have an enhanced area of reflectivity, generally greater than 15 or 20 dBz, that shows up as a semicircular region where you're sampling your debris. And the reason you would look for reflectivity is because your ambient CC would be homogeneously low across the whole area, so you wouldn't be able to pick out a lower CC signal. The location of the plume, of course, look for your rotational couplets. I'm not saying don't look for those, but expand that area to other areas that we as meteorologists know are favorable for a tornadogenesis, especially along convergence zones. Tornadoes love baroclinic zones. They love QLCSs. They easily can spin up along those. And there are many times that our radar overshoots any of those signatures or just is too broad. So we may see these semicircular CC depressions without a couplet. And then also, I know Ray is listening. I'm going to put in that spectrum width max. Spectrum width is a wonderful tool to look for these circulations that may not have an actual couplet with them on SRM, but spectrum width will show it sometimes, not always. And then look for the trend. See if this is a bottom-up process that spreads upward and outward with time. Now, this last aspect requires either a vertical continuity or temporal continuity with the radar signature. And if for warning operations, time is of the essence. So I would reserve this last aspect, this trend aspect for the plume, only in lower confidence situations. So now we'll go through examples. The rest of the talk is pretty much examples here. Putting it all together, this is an example from an HP supercell. We're going to start off here looking in the RFD region, this broad RFD. You'll see that we have a juxtaposition of higher reflectivity. We have a noisy CC signature there. It's very noisy. I wouldn't pick much out of it, but we do see a tightening circulation starting to develop here along the convergence zone, which is highlighted by spectrum width. We go to the next scan, which is a sail scan. We suddenly see the sudden circular fallout in CC with a much more tighter couplet, and there's your spectrum width bullseye. This is a beautiful example of that. And then just 3 minutes later, this is the next full volume scan. You can see that CC signature is widening out. The couplet is not nearly as pronounced as it was earlier, so maybe it's starting to dissipate, as well as your spectrum width signature isn't quite as robust as it was earlier. But quite honestly, all those product-based thresholds for looking for TDSs would have already worked here. So let's go to a harder case. This was an easy case. We're going to start with a more supercell type structure here. Starting off here, the blue line is actually the tornado track. I'll give that hint away right away. We're starting off here before the tornado touches down, and you'll see here, this is our supercell with the elongated appendage and RFD hook right there. You do have a broad circulation showing up there as well, but nothing really to write home about in terms of correlation coefficient. And then if we look aloft, just for reference, this is at the top two images are 0.5 degree and the bottom two are at 1.3. Nothing really exciting to write home about there as well. We move 4 minutes ahead, and all of a sudden things get a little bit more interesting, actually a lot bit more interesting. you'll see we're still looking at that appendage of the storm where we expect if there was going to be a tornado, there would be in this environment. And you'll see there's actually been a slight uptick in reflectivity up to about 40 dBz right at the center there. You still have your really broad mesocyclone that you're sampling there, but nothing really screams tornado. But notice right where that reflectivity spike occurred, your CC fell out very, very quickly. It went from about 0.97 and now it's all the way down to 0.7. And there's an area of enhanced spectrum width right there in that hook as well. So suddenly we're matching the shape and location aspects of the TDS identification technique as well. But I don't know of many meteorologists who would confidently issue a tornado warning off of this if they didn't have one out already. So let's go and see if we can fit that trend, match that trend part of the identification. Moving over to the next full volume scan here, a couple minutes later, you can still see that appendage is still sitting there. Still have that nice little solid CC fallout there that's juxtaposed with that 30 dBz little nubbin right there. And spectrum width isn't too exciting, but if we go aloft, this is where it gets really interesting, is suddenly that CC fallout is now showing up at 7,000 feet. That wasn't there in the previous scan. Reflectivity values are still solidly in the 20 to 30 dBz time rate, range. So we can confidently say that the trend, this upward ejection of debris is happening now. So it was in an area of the storm that we knew was favorable for tornadogenesis. The shape is confidently looking like a TDS, and now it's showing vertical continuity. So we can check all three aspects off the list as well. And over time, you'll see this plume, actually this little debris ball got completely separated from the storm updraft itself and just persisted onward and onward. And quite honestly, I'm not sure I'd even call that a couplet anymore. That's visible on radar. Spectrum width is really showing up quite nicely. You see a nice tight spectrum width bullseye there, but storm relative velocity, this isn't really showing it. And so this is just a cross section through that plume of that previous radar scan. You can see how displaced it is from the actual supercell in and of itself. And photos of the tornado at that exact same time show that exact same philosophy, with the RFD having cut all the way around the tornado, and the tornado is basically existing by itself, separate from its parent storm. And then finally, towards the end of the tornado track, you start seeing a widening of that reflectivity maxima as well, but really there's just no discernible couplet. So previous methods might not have called this a TDS, even though the behavior matched the lack of a couplet, even though we were in the right area of the storm, really wasn't there. So now this is a really amazing example here. I'm picking on Des Moines again. This is my old stomping grounds, but this is from July 19th, 2018, just east of Des Moines. We're going to look at this convergence zone shown here in the dotted line as this developing supercell is growing. And we're going to zoom in particular on this area where there's a bulge in the actual convergence zone, this more synoptic boundary moving through. And we do see this really weak supercell starting to develop, but keep an eye on that. If we look aloft, this is now at that same time looking at 0.9 degrees, you can actually see this really, really narrow RFD appendage extending all the way back, crossing I-35 there, and you can just basically almost see a hook echo right there. And we're only looking at about 600 feet above the ground there, and it lines up exactly with that boundary. You look on the SRM, there's just really nothing there to write home about, and the noise, the CC signature is quite noisy that close to the radar. There's just not much showing up. And then suddenly, in that area where that hook echo was, you see this really, really tiny increase in reflectivity. And if you want to squint, you can say there's probably some sort of small couplet there, but it's pretty weak. CC isn't much help here because you're just so, the reflectivity, the signal is so noisy over there, and spectrum width doesn't show much. But theoretically, we're ticking off the first two boxes of what could be a TDS there. But again, are you really confident to issue a tornado warning based off of this? Probably not. Moving forward in time, we see that signature is actually just starting to broaden off a little bit more. The velocity signature and CC signature aren't really anything exciting to write home about. So we can probably start ticking off the trend box here. All three aspects are being met there. Your reflectivity is about 40 dBz now on that tiny little reflectivity ball there. Moving forward, one more scan, it kind of looks like it disappears, and it really didn't disappear. What happened was the clutter filtering from the radar accidentally overrode it. If you went up to the 0.9 degree tilt there, shown in the top left, you'll see the signature is still there, and it's broadening out as well. The debris ball is still there at the next volume scan, but take a look at the convergence zone there. It's gotten very, very complicated just to the south and east of that initial TDS right there. You can see multiple inflection points starting to develop there. And actually, if you thought about it, if we had a cycling supercell, you could see that the new RFD could be wrapping in and intersecting with this boundary here. We also see this really interesting signature here, this comma head. This is actually the RFD showing up here, the density gradient. I'm not sure if this is actually precipitation or not, but you can actually see the density gradient, the baroclinic zone of the RFD showing up here on radar. It's just a beautiful signature that shows up here over the next few scans. And even to the south, we start seeing an additional baroclinic zone starting to develop there from a supercell that isn't even visible on radar yet. This was just a fascinating event to see in terms of how the storm morphology worked this close to the radar. But over time, you could see that what was a comma shape suddenly just turns into a solid ball. And so suddenly that should get our attention that something more interesting is going on there at this point. The tornado has been in progress actually for the last 5 minutes, but the circular area of higher reflectivity should be getting our attention there. It intersects with where we see that boundary sitting there with the storm. And you can actually see maybe a slight difference, a slight fallout in CC there, but it's really, really subtle. And you can see now we possibly have 2 TDSs simultaneously with this enhanced wind surge over by Bondurant as well. And at one point, the TDSs seem to have disappeared at the half-degree tilt. But again, this stresses that half degree isn't always the best to look at, especially if you're close to the radar. And quite honestly, when this radar image was taken, this is the webcam image from the I-80 right there, just east of Des Moines. Both tornadoes were still very healthy and very going on at this point. And then over time, the southern TDS got much more organized. You can see this very solid uptick in reflectivity up to about 50 dBz as it went through the town of Bondurant right there. Again, you just don't even see anything in SRM at all to call this signature a TDS. And over time, that signature actually started broadening out more, and you can probably more confidently call this a TDS now. The northern TDS really doesn't look all that great, to be honest with you, and it keeps going. Again, there's no couplet. There's no couplet anywhere to be found here at all. It would just fail previous methods. And it keeps going. It keeps going. And then finally here, about 10 minutes later, you start seeing a more classic reflectivity ball starting to develop here after the tornado has dissipated, quite honestly. Nothing even close to being sort of a couplet on SRM at all, and CC isn't much help here given how noisy the data is. But again, no couplet whatsoever. So hitting on that aspect where we are identifying TDSs with no couplets, which would fail previous methods. And this is just such a great example of going back to the original base products with reflectivity and in some ways SRM to diagnose the storm structure, kinematic fields, and even the TDS itself when dual pole dual pole can simply be used as a means of confirmation. It also shows utilizing more than just the half-degree tilt to look at storm structure and TDS structure, thinking sails and Merle as well. And then also it hits on the dynamic nature of the debris plume, especially if you're close to the radar, is that debris plumes aren't constant, and they may sometimes grow and shrink with time, especially these really, really close TDSs to the radar. Here's just some other examples I have here on my slide set. This is an example of a TDS where it was a grand total of 6 super res pixels in size. The average CC was about 0.9 or so, which would have failed the threshold methods that usually use about 0.8 or lower to diagnose the CC signature as a TDS. This is with the QLCS in central Iowa. And this is where the storm surveying aspect ties into the TDS talk, is because without the aerial surveying means, I wouldn't have the confidence to come forward and say that was a tornado. But when we got the aerial data up there, the satellite data, the drone, we could actually see this really tiny narrow area of path through the fields here, probably only about 5 meters wide. It went through a farmstead and it knocked off a grain bin and some tree limbs, but overall it was a really tiny tornado as well. And this is another great case, lovely, lovely case from Western Iowa from October 23rd, 2015, where a case where land cover and the environment played a role in what we saw for the TDSs. And just looking at the ML CAPE and effective SRH, you really wouldn't be expecting robust updrafts with only about 100 to 200 joules per kilogram of ML CAPE, but the effective SRH gets our attention as we have this synoptic cold front working through the western part of the state here. And this is basically a composite of the storm as it moved across western Iowa. It's a bit busy, but the far left-hand side of the image is starting at 23Z, going all the way to 4Z at the far right-hand side of the image. And what we saw, which was just bizarre, was over time, the northern part of the storm, north of this bow apex, experienced downscale growth into discrete convection instead of a line. Very, very interesting. And these lines denote the individual cell tracks. And with that, we saw little debris signatures on radar with them. And there wasn't even any lightning with these storms. The farthest east the lightning got was this dotted line in west. And there was no lightning with any of these circulation paths that we saw. One of them actually hit a farmstead and caused rateable damage. Others had longer paths and caused actually some debris scouring in the fields. It was just an amazing event. And these storms were very shallow. These storm tops are probably about 14,000 feet or less. And the TDS heights extended up to 10,000 feet or more. They covered most of the storm depth. And there really wasn't much in the way of a rotational couplet. You can say there was one there, but it certainly wasn't tight as well with these, maybe call them mini supercells. It's really tough to classify what these were. But in general, again, we saw these CC signatures extending really high up into the storm, and some of the early work on TDS height versus strength may have said this was an EF2 tornado, which simply wasn't the case. It was likely the fact that we had a lack of hydrometeors and the dry corn stubble being lofted up into the air was a factor in what we saw with these TDSs as well. It was just a very bizarre event that just as bizarre to this day. Other signatures you may see from a TDS, one of the newly coined signatures is the debris fallout signature. What happens is basically the debris goes up and then the debris comes back down somewhere else in the storm. This is an example from western Missouri on May 28th, 2019, following our Lawrence tornado. This example, we have a very strong tornado going on right now just to the east of Kearney. But over time, what happens in about 10 minutes, we suddenly see this second broader area of CC suddenly appear to the north of that TDS. The tornado is still ongoing, but this second area, the second fallout, falls out behind the convergence zone. It's not an area that we would see that's favorable for tornadogenesis at all. And over time, it advects fairly quickly to the north while the tornado itself dies off. And just from a first glance at half degree, we wouldn't see much of a connection between these signatures. But if we go up, do a volumetric look at these signatures, starting with half degree in the top left and going up to 1.3 on the top right, 1.8 in the bottom left, and then eventually 3 degrees, you'll see a connection between these plume, these two CC signatures. So you can actually see almost like an arch. You can visualize an arch of debris moving up around the storm and then descending along the north flank of whatever mesocyclone was up there. Really, really exciting stuff to see there. A more just bizarre debris fallout signature. This is with a LP Supercell in Iowa in 2014. This is during the tornado itself. You can see a very solid TDS there just south of Buckingham. We go forward about 20 minutes as the storm begins to eventually decay. The tornado has since dissipated. You'll notice on the CC, you start seeing more of a speckled appearance to the mid to upper levels of the storm updraft. And then over time, this is about another 15, 20 minutes later, you'll start seeing this bizarre CC fallout throughout the entire storm. And then within an hour later, all that's left of the updraft, this orphan anvil essentially, is this low CC. And from what we can tell, this is corn debris. The EM that was following this storm said it was raining corn debris for many, many minutes after the tornado dissipated. So it's probably not true corn debris, corn leaves. It's probably more dust-like, but it's just a bizarre signature that we saw going on there. And so some caveats to TDS identifications. The biggest one I can name is updrafts and inflow regions. They are a bear to try and determine TDSs versus updraft versus inflow. They tend to be slower evolving, non-circular, and generally possess lower reflectivity values than a TDS. And this is where monitoring the trends in the signature is so critical and watching how the signal evolves. Here's an example from a QLCS. We're during a tornado. The tornado was just visible as one gate-to-gate couplet there at best, if you even want to call it that. The convergence zone, the inflow region is shown here in this vertical part of the CC signature there. And you'll notice after the next scan, you'll see this sudden fallout, this more circular CC fallout region here in the area of much higher reflectivity. Originally, this lower CC is in an area of about 20 to 30 dBz and matches the shape of the higher dBz contour. But then you'll see this circular fallout here. That's your TDS actually. And you can see on SRM, it's very, very tiny couplet, and we're not that far away from the radar itself. Going forward one more time step, you'll see that signature is still there. It's broadened a little bit more, and you can still see it kind of attached to this convergence zone. And if we went up, doing some more vertical slices, going upward with time, this is the 0.9 tilt at 3,400 feet. You can see we're getting a little bit more on over the convergence zone, but the TDS is showing much, much better up there in a more circular CC fallout region. And then finally at 1.3 degrees at about 5,000 feet, you can see the debris plume is starting to widen out and dissolve up there, but it's still circular in nature, and we're above the convergence zone. Radar artifacts such as non-uniform beam filling can pose an issue, but again, looking at the trends in the signature and tracking these signatures, there's actually two different TDSs right there embedded within this non-uniform beam filling mess. Spectrum width really helps out there, and you can even in this low top supercell regime see the circulations there as well. Mixed hydrometeors, especially hail, they tend to be slower evolving, kind of like updrafts and inflow regions, and maybe you can sometimes trace them to the mid-levels of the storm and descending downward. They're oftentimes more diluted than the sharp gradations you see with the TDS. So wrapping things up here, the big things to look for are the three big things are the shape of the signature, where it is located in the storm, and how it behaves with time. And this is just really trying to advance beyond the product-based thresholds. It's not saying that the product-based thresholds are wrong in any way. They've done great for us. But we as meteorologists are trying to find the tornado, trying to find all the tornadoes that we can as best possible. And so this pushes beyond that simple product-based technique. If you have a tornado threat, activate the best scanning strategy to help see both the tornado development and the TDS, whether it's mesoscales or Merle. And then finally, when it comes to office operations, utilizing the raw correlation coefficient is something I've hit on for many years, and hopefully everyone's using that by now versus the smooth level 3 stuff that is by default sometimes shown in AWIPS. It's immensely better at helping to find these smaller TDSs, and maybe even sometimes in warning operations, have a second set of eyes looking for TDSs, especially in very prime environments like high shear, low cape scenarios where these things can be subtle and fast evolving. And so final thoughts, we really are resolving TDSs at the very lower bound of the tornado spectrum. And there are valid questions that remain if all of these are tornadoes, and that's why it's, you know, the storm surveying aspect and the aerial data aspect has really helped push the confidence in what these signatures are be much, much more than it was even 5 years ago. And as Walker put it, you know, these events put warning forecasters in a bind, and they're very short-lived, usually low impact. Most of the time, you'll never even hear about them, but there's always the fear of missing the one. And we all know, we all have what the one is in the back of our mind. And these can be very, very difficult to verify. You know, the public perception, if we're just throwing out tornado warnings on these and we never hear about them, is that a good thing? And so the question becomes, how do we communicate the threat properly? And that's something that we as an agency are going to have to come to terms with at some point. But identifying these and cataloging these features only help push the science forward. So that's how these two talks kind of combine together, is pushing the science forward to helping us as an agency figure out what to do with these, and maybe even go to more of an impact-based warning system versus a phenomenon-based warning system that we use right now. So with that, I will wrap up and take any questions.